have a yo-yo. What's it made of? This is like one of those really, really cheap yo-yos. It's just cheap old plastic. Nothing very exciting. So let's hold it. I weighed it earlier. The mass of this yo-yo is 30 grams. I'm going to hold the yo-yo so the radius that it will move in is 60 centimeters. Okay. So get the yo-yo spinning. It's not moving in a straight line. Therefore, there must be a net force acting on it. What force is the centripetal force in this example? Tension. If the string were to break, this would move off, the yo-yo would fly away, initially heading tangent to the circle, moving in a straight line. So let's go ahead and say, I don't know how fast I'm actually spinning it. Let's pretend I'm spinning it at 1 revolution per second. So it makes 1 turn in 1 second. Seems fair enough. I would like to know if it makes 1 revolution in 1 second, I would like to know the tension in the string at the top and at the bottom. Okay. So let's just draw. Here's my yo-yo. It's moving in a circle. Yeah, I can't draw circles very well, sorry. We know the radius of the circle, and we know the mass of the yo-yo. It's moving in a circle, therefore it has a centripetal acceleration. When the yo-yo is at the peak up there, what direction is the centripetal acceleration in? Towards the center, so straight down at that instant. So there must be some net force resulting in that acceleration. So let's draw the forces on my yo-yo. What forces are actually acting on my yo-yo? Tension? What direction? Strings can only pull, so it has to be pulling downwards. Sure, there's gravity. That's always downwards, towards the center of the circle. This thing's not moving fast enough for drag to be significant. If you really wanted to include it, it would just be opposite its motion. Okay. We need to choose the coordinate system so that towards the center is our positive direction. So we can use a traditional XY coordinate system, but we need to call down positive. Either that or we need to call the acceleration negative. You can do either one. I find that I forget to make my acceleration negative. Just knowing my own limitations, I tend to make towards the center positive regardless of which way it's pointing. So adding these vertical forces, we have the force of tension towards the center, and we have the force of gravity towards the center. Both of them together make up the centripetal force. They are centripetal forces. Together they are determining the centripetal acceleration. Adding those together, those will equal the mass of our yo-yo times the centripetal acceleration that our yo-yo has. Now we know force of gravity is mg. We know acceleration is v squared over r. Solving for the force of tension, force of tension will be mv squared over r minus mg. We know the mass, we know the radius, we know g. We need to figure out v. Now we know that this yo-yo is making 1 revolution in 1 second. But v, speed, needs to be in meters per second. One revolution is how many meters? 2 pi r. It's just the circumference of the circle. It completes 1 circumference of the circle in 1 second. So the speed, v, will be 2 pi r over 1 second. So 2 pi, the radius is 0.6 meters. .77 meters per second is the speed that it's traveling at. So we can put that in over here. The mass is 30 grams, so that's 0.03 kilograms. I'm going to factor that out. So v squared over r, so 3.77 meters per second, that's squared, over r, minus, I pulled the m out, so minus g. .42 newtons. Not very big at all. It wasn't hard to keep that little guy moving in a circle. Doesn't exert a whole lot of force. Now this is at the top. The tension will not be the same at the bottom. Can you imagine why? Right, at the bottom, the tension and gravity are in opposite directions. So at the bottom, we're going to have force of tension minus mg equal to mv squared over r. So force of tension will be mv squared over r plus mg. So gravity is counteracting the tension. That's convenient. 1 Newton. So it's greater at the bottom than at the top. At the bottom, it not only needs to accelerate the yo-yo ball, but it also needs to counteract gravity. So this force of tension is the combination of accelerating it and counteracting gravity. At the top, the tension has help from gravity. So it doesn't even have to provide the whole acceleration by itself. So the tension is smaller at the top.
So if you turn that into a bungee, it'd stretch a lot longer to the bottom and so it'd turn into an ellipse.
Yep, that's true. It would be elliptical. If we could attach it to some sort of bungee type cord. it would be an elliptical motion. How would we find the force of tension if it was off at the side? Is gravity contributing to the centripetal acceleration right there? No. It has no component towards the center or away from the center of the circle. At this instant, gravity doesn't play a role. At this instant, the force of tension is the only one causing the acceleration. If we're down at an angle, then we'll have to break it into components, yes. So we'd have force of tension towards the center, force of gravity straight down, but we'd need to know the component along the line that goes towards the center of the circle. So we'd need to know the angle it's at. So whenever you're dealing with problems with centripetal acceleration, any sort of turn or curve, you always want to look at some of the forces along the line that points towards the center or away from the center of the circle. That's all you want to look at. Okay? Now, have you ever ridden on a ride that goes in a circle? For example, the Colossus at Lagoon. You ride around, you go upside down, come around. You feel like you're getting pushed into the chair. But there's no physical force pushing on you into the chair. They call it a centrifugal force. It's not really a force. They call it a centrifugal force to make it make sense in terms of, as far as you're concerned, you have no acceleration because you're not going anywhere. But there is no physical force pushing you into the chair. So why do you feel like you're getting pushed into the chair? Your inertia. Exactly right. Your body has mass. According to Newton's first law, an object in motion will stay in motion unless a force acts on it. Your body wants to continue in a straight line. The roller coaster car happens to be in the way. It's not letting you. So your body wants to go in a straight line, but the car's forcing your body in a circle. So that's why you feel like you're getting pushed into the chair.